Hi guys, well, welcome to our first, I guess, online lecture. For now, for this first lecture, I'm obviously doing just an offline recorded lecture. The next one will be on Zoom, which will be a live lecture, and so you can connect and basically follow me as I'm covering the topics. After that, I guess we can decide. We'll see how either one of these go. I mean, ideally, we should continue with the Zoom so you guys have a chance to ask questions as we go. Okay, so before I actually start the next topic, which will be alpha halogenation reactions of enols and enolates, I just wanted to look at a few examples. So I have a few examples here where we have the initial ketone, and we have different bases, and we'll try to predict what the enol or the enolate products are from these reactions. So if we look at this first example, you can see here we have several different positions that could be acidic. So I'm gonna draw those acidic hydrogens. So the first one is here. There's another one here, and there's another one here. So these are the three hydrogens that are alpha to a carbonyl group. So if we compare these three hydrogens, you can see that two of these, this one here and this one here, they're alpha to only one carbonyl group, right? So this one and that one. But the one in the middle, this guy right here that I just circled in green, is flanked by two carbonyl groups, right? So one here, the other one is there. So that should be the most acidic proton. So in these scenarios, whatever base you use, you will form the same enolate. So if we are to draw the enolate now, that should be so our six-member ring flanked by another six-member ring. So then we can either write it this way, sodium. And if you decide to deprotonate and write it the other way, that's also fine, right? Because we can write the tautomer of this, where that bond moves here, this moves over there. So either one of these should be fine. So in this case, we'll have O sodium here, double bond, and over there. And I apologize for a little bit of ugly handwriting. I'm getting used to writing on a tablet. So, all right, in the second conditions, now we have again two different hydrogens that we can pull off using the turbotoxide base. So first one is here, and then there is another one that is over here. So now, which one will we pull? First of all, in the last lecture we talked about kinetic and thermodynamic enolates. So basically, we've talked about that if the deprotonation is rapid and irreversible, so that happens when we use bases like LDA, then we get the kinetic product, so which is basically defined by the sterics. But if you use bases such as turbotoxide, especially in a solvent like T-butanol, that deprotonation is reversible, so then it will equilibrate to the thermodynamically most stable enolate. So if we draw the two possible enolates here, so let's say the first one I'll say is, oops, sorry. First one will be this enolate. And I guess the second one is the enolate to this direction. And if you compare these two enolates, you can see that over here, this double bond will be conjugated to the phenyl ring, right? So that means thermodynamically this will be a more stable olefin because it will be a conjugated olefin. So so for that reason, this particular enolate here will be the preferred enolate under these thermodynamic enolization conditions. So if that's not clear, let me try to maybe draw here. So I'm going to try to draw here the same structure in the more elaborated fashion. So that's our phenyl ring and the double bond. I guess I can just write the potassium. So you can see now that this double bond here is conjugated to the rest of the phenyl ring. Okay. This next scenario is actually fairly simple. So if I'm to draw this this ketone here, so that ketone looks like looks like this. So there are no hydrogens on this side, so you'll only have hydrogens on the other side, and you're using LDA, so that will be just simply the corresponding enolate. So you will have phenyl, so you will have the lithium CH2 here. Alright, this last one uses acidic conditions, so remember that under acidic conditions, so I'll just write here, under acidic conditions, we get thermodynamic I guess thermodynamic enol, right? Because in this case, under acidic conditions, we won't form the enolate. So, and the thermodynamic enol is the one that has the highest substitution, okay? So, in this particular scenario, that thermodynamic enol will be OH, and we have the two methyl groups here. So remember, under acidic conditions, right, you cannot write an O minus, right? So it has to be an OH, so it should be an enol, okay? So this will be actually very important for our next discussion. So I'm gonna leave this one here and switch to a different project. Alright, so what I'm going to do is I'm just going to open a new page. Alright, and here we're going to talk about alpha halogenation of enols and enolates. Alright, so first let's just write the reaction. What's the reaction we're talking about? So we will start first with reactions of enols. I'll say enol halogenation. And the reaction is that we have, for example, cyclohexanone. We treat it with bromine under aqueous acidic conditions. And what this will do, this will form an alpha bromo ketone, right? So remember, this is the so right here, this is the alpha position, right? And we have a bromide there. So let's look at the mechanism, how this reaction happened. And this is, if you remember at the beginning, we talked about that these alpha functionalization reactions, right? When we introduce a functional group to the alpha position of a ketone, they always go through an enol or enolate, because by themselves the alpha positions of ketones are not acidic. So in terms of mechanism, what happens here is first under acidic conditions, this ketone will undergo enolization. So we have an acid, and the ketone has a lone pair. So we'll protonate the ketone to make these positively charged species. Then here water can come in, pick up that proton, and quench the positive charge, which will create our enol. Now once you have the enol, now it can react with electrophiles such as Br2. So it simply attacks this electrophile and kicks out a Br minus, so minus Br minus, and it will give us this initial intermediate, which will look like, this. And now in the final step, we have this Br minus that can come and pick up the proton to give us our alpha bromo cyclohexanone. Sorry, that's an ugly Br. And plus a molecule of HBr. And this HBr molecule here is kind of actually important, because if you see, the reaction starts, or reaction requires to have an acid, right? But at the end of the reaction, it also generates a molecule of acid in the form of HBr. So that means this HBr here can actually go back and catalyze the, so I'm just going to do this, it can go back and catalyze the reaction itself. So these type of reactions, we call them, they are autocatalytic. So this is an autocatalysis. So basically the reaction by itself also generates the catalyst. Alright, so this was a simple example of a symmetric ketone, right? So for the cyclohexanone, basically the two positions, so two sides, either it's this side or the other side, they're equal. So what happens when they are not equal, right? So that will be our next topic. So when they are not equal, what will happen is the following, right? So let's look at an example of, for example, a methyl substituted cyclohexanone, okay? So in this case, if you remember, we talked that when under the acidic conditions, we will always form the thermodynamic enol, which is the higher substituted enol, right? So which means you will form this enol, and then when this reacts with the Br2, it will give you this higher substituted alpha bromo ketone. Okay. All right. So what good these alpha bromo ketones are? So what can we do with them, right? So it turns out that we can actually treat these compounds with base, and you have basically a lot of bases to choose from. So pyridine is, for example, one. So if you treat these with pyridine, they will undergo an elimination reaction to form these cyclohexenones. All right, so let's try to maybe use this in an example, right? So let's say I've given you well, let me maybe choose a different ketone, right? Let's say I have given you this kind of a ketone, and I want you to convert it to so that's up. I want you to convert it to this particular compound here. So if we were to do a electrosynthetic analysis on this compound, so when we have a 6-member ring right here with a double bond in it, it should signal to a possible Diels-Alder reaction, right? So if we do a disconnection for Diels-Alder reaction here, what we would get is following, right? So we have a if we disconnect for Diels-Alder, you can see that if we have this particular dienophile and this diene here, they can react to give that compound, right? So now the question is, how do we make this one right here? And we can make that from that particular from this ketone, right? By using our halogenation method that we just learned. So if we treat this with Br2 under acidic conditions, first we will get the first we'll get this, and then we can treat this with pyridine to get to our to the ketone that we were trying to get. Okay, so that's an example of applying the chemistry that we just learned, connecting it with our previous knowledge. just take a... Alright, so similar to the ketones, also carboxylic acids can undergo alpha halogenation. So this is, in this reaction, we'll say alpha bromination of carboxylic acids. So in this reaction you have let's say a carboxylic acid, something like this, and you treat it under the same conditions. So we still have the, actually it's not the same conditions. So for the alpha bromination of carboxylic acids, we'll use a slightly different conditions, in a way that we'll use Br2 and PBr3, which will initially actually give us this compound, but if we treat this with water, the net reaction is just making the alpha bromo carboxylic acid. All right, so if you can write this in a one step if you want. So you could just write 1 Br2 PBr3 and 2 H2O. All right, let's look at the mechanism of this reaction, right? So how does this happen? So before that, I want to remind you guys one reaction that you have learned last semester, which is that if you take alcohols and treat them with PBr3, you will form bromoalkanes, for example, right? So this reaction that we're looking at, the first step is actually pretty similar. So you take your carboxylic acid, and there's that OH group. So if you treat this with PBr3, it will first form a bromo-carboxylic acyl bromide, right? So that's the acyl bromide. So then this actually now behaves like a ketone, so it can undergo an enolization reaction. So it will give this enol, which then reacts with the Br2 to give you the alpha bromo, this acyl bromide. When we covered the, for example, acyl chlorides, we said that when you treat acyl chlorides, and similarly here acyl bromides, with water, they undergo hydrolysis. So that's basically the last step in this transformation. Okay, and also this reaction actually is a name reaction. So this is called the Hell-Wohlhardt-Zielinski reaction. Okay, So this is actually the only halogenation reactions that I wanted to cover under the acidic conditions. So in the next part, we'll look at the halogenation reactions under basic conditions, right? All right, so under basic conditions, the reaction occurs somewhat similarly, although it's going to be a little different for some of the ketones. So let's look at, let's say this is the alpha halogenation under basic conditions. So if we use a similar example to the cyclohexanone case, so in this case I'm going to use this dimethyl cyclohexanone. So if we treat it with the same Br2 sodium hydroxide, initially you form this alpha bromo cyclohexanone. The one problem under basic conditions is that once you insert one halogen, like you just insert one halogen here, this proton now becomes a lot more acidic compared to that initial proton, right? Because you have an additional, here the only electron withdrawing, in the first case here, the only electron withdrawing group you have is this carbonyl group. But in the product, you have the carbonyl group, and you also have this halogen, right? So they're both electron withdrawing groups. So that makes this proton in the product more acidic compared to the proton in the starting material. So as a consequence, this reaction is very hard to stop at monobromination. So it will actually undergo another bromination to form this dibromo derivative. So in a sense, this is a little bit less practical, right? Because you can't stop it at monobromination, but if you want to get a dibromination of a ketone, then you can actually do that, right? So one thing I'll mention is you should be careful when you're trying to use this halogenation under basic conditions, because if you have, for example, so if you look at here, I have two methyl groups flanking that carbonyl, and I did that purposefully because if you don't have it, if you just take, for example, simply cyclohexanone, I'll move this up a little bit, and try to do the bromination under basic conditions. Now you have protons on this side and you have protons on the other side. So you will basically get a mixture of bromination products. All right, but there's one area, actually, one application of this reaction which is very useful, and that is if you have, for example, methyl ketones where on the other side there is no no protons, like a phenyl group, for example, right? And you treat these with bromine, sodium hydroxide, so this is an excess of both reagents. You will get the sodium salt. So now we have inserted this oxygen here, right? And after you acidify it, now you will get the corresponding carboxylic acid. So how does this reaction work? So this is actually another name reaction. We call this a haloform reaction. And in case when you're using bromine, this will be a bromoform reaction. Because the side product in this reaction is this, which is the bromoform, right? So that's the bromoform. All right, yeah, let's use this bromoform reaction and look at the mechanism of this alpha brominations under basic conditions. So if I use the same ketone, what will happen is in the first step, so you treat that with sodium hydroxide, that will enolize it to make sodium enol ether, or sodium enolate. Then when we treat that with Br2, this will form the first alpha bromination. And now we treat that with another OH minus, which will again enolize it to give us the second enolate. And then this will again react with sorry, sometimes putting dots is like the hardest part of writing on the keyboard, on the all right, so that's the lone pair, very ugly lone pair, but it is a lone pair. So that will now give us this. And you reacted with one more equivalent. So I'm gonna skip the enolate formation and all that. So you form this and the CBr3. So now once you have this intermediate, now this carbonyl here is very electrophilic because it is a carbonyl, so carbonyls are electrophilic in general, but now you have this CBr3 group attached to that position, so that makes it this blue dot position very electrophilic. So as a consequence of that, and we have an excess of OH minus, so that OH minus will attack the carbonyl now. To make a CBr3. And now the CBr3 here is a good leaving group, so it can basically leave to give us that. And then we have a CBr3, which can pick up the pick up the proton to give us our carboxylate. Okay, so that's the mechanism for the haloform reaction. So before I finish, I want to draw your attention to one thing, right? So if you remember, so in this case, if we have a phenyl methyl, so we do the haloform reaction, right? Br2, sodium hydroxide, and we get this carboxylic acid, right? So in a way, we just inserted an oxygen atom between the carbonyl and the methyl, right? So this is in a way in contrast to another reaction we've learned, right? So when we learned, for example, a Baeyer-Villiger reaction, MCPBA, we were inserting an oxygen between the phenyl group and the carbonyl because phenyl had a better migratory aptitude, right? So I think that's an interesting kind of a connection to that one, right? So depending on which side you want to introduce, so depending on if you want to introduce to this side or the other side, you can use these two methods. Okay, so that's our first try on an online lecture. I hope it wasn't too confusing. So next time I think we're gonna try to do this over the Zoom, and hopefully that will be a little bit more interactive. All right, I hope you guys are staying safe. Yep, that's it.